Hello everyone. So welcome to the AnalogX. Uh, Today we will solve this numerical problem. Okay, so they have given consider the current mirror shown below, where input current is 100 microampere and each transistor has a W by L ratio of 10 micrometer by 0.4 micrometer. Okay, so what will be the change in output current for a 100 millivolt change in output voltage? Okay, so they have given the width and length ratio, so that is 10 micrometer by 0.4 micrometer. Okay, and they are changing this output voltage. Suppose there is some kind of load, or you can assume as here a differential input pair. Okay, so and now they are biasing this one, any kind of their circuit, due to which this node is changing by 100 millivolt. Okay, so how much this current will change? Okay, so we know that for this simple current mirror, I out by I reference will be W by L and 1 plus lambda VDS. Okay, so since their width and length are same, so that will be cancel out. And okay, let me write completely 1 plus lambda VDS. VDS is V out and divided by W by L 1 plus lambda, this one VDS, that is VGS. Okay, so this will cancel out, and for a technology lambda is equal. Okay, so this will be, if you will send this to numerator and then solve, then it will come as lambda delta VDS. Okay, so this is our I output by I reference. So you can do this math. It's that's easy one. And after here you need lambda, and delta VDS is 100 millivolt. Okay, so that is 100 millivolts, and we know that R equal to 1 by lambda ID. So okay, so they have given here del lambda into L. Okay, so we don't need to find from R. So they have given lambda L equal to 0.16 micrometer per volt. So from here they have given length equal to 0.4 micrometer. So lambda will be 0.16 micrometer per volt divided by 0.4 micrometer. So that will come as lambda equal to 0.4 volt inverse. Okay. So now put this value. So that will be I out equal to I reference is uh, I reference is 100 microampere. Okay. So this one is 100 microampere into lambda VDS. So lambda is 0.4 per volt and VDS is 100 millivolt. Okay, so this will come as 4 microampere. Okay, so that will come as 4 microampere. This will be like 0.4 0.4 millivolt, and then you will multiply that one, so that will come 4 microampere. So now let's analyze this circuit further. Okay, so let me draw this circuit. So this one is, this is my current mirror. Okay, and this is biased by a current of 100 microampere. Okay, so this transistor is working as I to V converter, and this transistor is working as V to I converter. Okay, so what will be the output resistance? There will be some output resistance of this transistor. Okay, so and this there is one, this internal current. Okay, so if this node is changing, okay, if this node is changing by some amount, so where that current will flow, that current will definitely flow through this resistance R, because this is dependent current, this won't change. So this is fully controlled by this VGS. Okay, so any change in that node will flow through R. Okay, So, and this will be VDS. So definitely that total I will be changed by this amount. Okay. So again, that change in current will flow through that R resistance. Okay. So the delta I out will be VDS by R. Okay. So what is delta VDS? That is 100 millivolt and R equal to 1 by lambda ID. Okay. So we just calculated above 100 millivolt and that is lambda is our 0.4 volt inverse and current is 100 micro ampere. Okay. So again, this will come as 4 micro ampere. Okay. So the point is here, any change here at node will flow a current through this output resistance of this branch, that is R. Now let's consider another case in which we will use cascode current mirror. Okay. So suppose this is our V2I, I2V. Okay. So that is our 100 microampere. Okay. And now this is my another MOSFET, and now I am cascading with one transistor. Okay. And suppose I'm getting some bias voltage here to bias this. Okay. Now we'll analyze the same situation where this circuit changing this node by 100 millivolt. Okay. So how much this current will change? Okay. So how much this current will change? Again, we will do analyze like this is our transistor. Okay, so this is VB, this is VB. Okay, so I'm taking this one and drawing here. Okay, and this is my I out current. Now, what will be the output resistance from here? From here, if we look from the drain, so we see R naught, and if we cascade, so that transistor will multiply this R naught with GM R naught. So total output resistance will be here GM R naught into R naught. So what will be the output current I out? Okay, so I out will be node voltage here, that is VDS divided by total resistance. Okay, so total resistance is GM R naught into R naught. Okay, now so again our delta VDS is 100 millivolt, and we have to calculate GM R naught. GM R naught square. Okay, so this equation is 1. So they have given some value, we will use that one. So GM equal to, we know that mu n COX W by L and V over drive. Okay, so I think they have given mu n COX equal to 190 microampere per volt square, and W by L is 10 micro by 0.4 micro. Okay, and this one is 350 nanometer technology. So just for illustration purpose, I am taking this V over drive as suppose 200 millivolt. Okay, so you can take anything, just we are just comparing the results. Okay, so this will, when you will calculate, so this will come as 9.5 into 10 to the power minus 4, that is 0.95 millisiemens. Okay, and what is R? R equal to 1 by lambda ID. Okay, so that is 1 by lambda is 0.4 volt inverse into ID is 100 microampere. Now let's put this value GM and R. So delta I out will be delta VDS or delta V out divided by GM R naught square. So delta V out is 100 millivolt and GM is 0.95 millisiemens, and that R will come as 25 kilo ohm. So put here 25 kilo ohm square. So this will give us 1.68 into 10 to the power minus 7. That is 0.168 microampere. Okay. Now let's compare both results. Okay. So this is our simple current mirror. So this is our 100 microampere, and let me copy this one, and we are giving one cascade here, cascode. Okay, so that one transistor mirror here. Now this one is our V out, and this one is our V out. Okay. So in this case, if I am changing my node, this one 100 millivolt, so my output current is changing by 4 microampere. Okay. And here output resistance is R not only. And if I'm changing here 100 millivolt, so my output current is changing by 0.168 microampere. So this will change as 0.168 microampere. And from here, the total resistance is Gm R naught square. Okay. So this is how we compare both results. So you can see clearly here impact of cascoding. We are increasing our output resistance, and hence our change in output current is minimizing. Okay. So you can I'm giving one follow-up question. You tell me, okay, comment down in comment section. Suppose this one is same I'm taking. This one is VB and this one is VB. Everything is given. You can use, if some data are missing, so you can use your own. Okay. So this is changing by 100 millivolt. So tell me what will be the change in this current. That is we already found out. Now change, tell me what this node, how much this node will change. Okay. How much this node will change. So I can give you one hint. You already know that I out. Okay. You just multiply by R naught of this transistor. So you will get, okay, let me do that. This is 0.168 microampere into R naught. 1 by lambda ID. Lambda is 0.4, ID is 100 microampere. Okay. So let me calculate this one. That it will come as 1.168 micro, I think, and divided by 0.4 into 100 microampere. Okay, so I think this is coming as 4.2 millivolt. Okay, so this is coming as 4.2 millivolt. Okay, so you can calculate also, and let me know if I calculated anything wrong in this question. Okay, so I hope it was clear, and please let me know if you feel any doubt. Okay, bye. Thank you.